Welcome back, everyone. On today's video, we're going to be talking about how we can solve ODEs that involve the Dirac Delta Function. This one is pretty straightforward. It's a function that's really similar to the unit step function. I did not put the graph in this moment, but instead of being a step like we see in the unit step function, which you can find the video here in the description, this one is used a lot more when it comes to impulses. So instead of having a step response, this is an impulse. At some point, it's 0. At a certain value of t, it just becomes an input that has a value of 1. And after it moves that point, it goes back to 0. So it's just like a quick input, a quick line that just appears in a function. So the Laplace of that one is also pretty straightforward. If you're taking the Laplace of the delta function, you can see here on the right side that it is just an exponential of the fraction of e to the negative as. And you can notice the difference that for the unit step function, which is on top of that one, it's the same exponential, but divided by s. But for the delta function, it's just exponential. So make sure that you do not confuse the two. They're pretty similar, but the unit step function, you divide by s. For the delta function, you do not divide by s. So that's a key difference there. So we have this problem here. We have y double prime plus 25y equals to delta t minus 4, where both initial conditions are 0. So once again, let's take the Laplace of y double prime, which is s squared capital Y minus s times y of 0 minus y prime of 0. But because both initial conditions are 0, I get only s squared capital Y. The Laplace of 25y is just 25y. And the Laplace of delta t minus 4 is just e to the negative. Okay, so let's put everything together. And you can see that we're going to get s squared capital Y plus 25y equals to e to the negative 4s. We factor out a capital Y, and we're going to have s squared plus 25, in the parentheses. We solve for capital Y, so we divide. And our final answer, well, not our final answer, our halfway answer, our answer in the Laplace domain is just capital Y equals to e to the negative 4s for s squared plus 25. Now, to solve this one, we need to take the Laplace inverse of that to get our y of t. So we take the Laplace inverse of all of that. And you'll notice that that exponential, I put it in green, it's our t-shift, right? Remember that. You can find that video here in the description as well, the t-shift. So that will translate into back to the t domain as the unit step function and multiply times, and the t substituted by some amount. So you can see that we can factor that one out, and we only have 1 over s squared plus 25 times u of t minus 4, where t will be shifted for t minus 4. And you can see that regardless if we started with the delta or the unit step function, and whenever you do the t-shift, it always corresponds to the unit step function, regardless if you started with the delta one. So just I want you to make that note that not because we're using delta at the beginning, it means that we also solve with delta. No, that's not how it happens. Delta just has its way, is exponential at the beginning. That's it. After this, it just plays back to the rules that we know so far. So continuing like this, you can see that this will be equal to sine of phi t over 5. That's Laplace inverse of 1 over s squared plus 25. And basically, if we just shift the t's for t minus 4 and multiply this 5, this is what we get. Y of t is equal to sine of phi t minus 20 over 5 times u of t minus 4. So this is a quick example of the delta function. You can see that if instead of delta, it would have been an u of t minus 4, then we would have to use PFD because our answer would have been e to the negative 4s over s times s squared plus 25. And then we would need to do a lot more things to solve here. All right, let's see another example. So this one we have y double prime plus 4y prime plus 4y equals to 2 plus delta of t minus 1, where y of 0 is 1 and y prime of 0 is equal to 0. So this one, as you can see, will turn out to be a longer problem, but not difficult nothing too difficult that we cannot solve. So let's continue. Taking the Laplace of y double prime, s squared capital Y minus sy of 0 minus y prime of 0. Substitute the values, and we get s squared capital Y minus s. Taking the Laplace of y prime, we get 4s capital Y minus y of 0. 4 multiplied times all of that. So we get 4sy minus 4. The Laplace of 4y is just 4y, capital Y. The Laplace of 2, it's 2 over s. Do not forget that. And the Laplace of delta t minus 1 is just e to the negative s. So we put everything together, and this is what we get. So from this one, we're going to factor out a capital Y. And everything that remains, we're going to send it to the other side. In a little bit. So you can see we have capital Y times s squared plus 4s plus 4. We have here also left the s minus 4. So we can send that one to the other side. It will become s plus 4 plus s over 2 plus e to the negative e to the negative s. So you know we need to solve for capital Y. So we'll divide everything by s squared plus 4s plus 4. Then it looks like this. And then this one at the bottom, we can factor it out. And we're going to end up with s plus 2 and s plus 2. So you can see here we have capital Y is equal to s plus 4 over s plus 2 times s plus 2 over s times s plus 2 times s plus 2 plus e to a negative s over s plus 2 s plus 2. So we can start doing a bunch of PFDs. We can do different things to solve this one. But let's apply all the tricks that we have learned before to make this problem easier. So to begin, to start, you can see that the first term, s plus 4, is over s plus 2, s plus 2. So one way to simplify that is to break up that 4 into 2 plus 2. So we have s plus 2 plus s plus 2. And because they both have, there's a sum at the top, we can break that sums into separate fractions. So we can have s plus 2 over s plus 2, s plus 2, plus 2 over s plus 2, s plus 2, plus 2 over s times s plus 2, s plus 2, plus e to the negative e to the negative s over s plus 2 squared. Well, we could have done the same thing on some of the fractions. I just didn't do it, but it's the same thing as s plus 2 squared, right? So we continue simplifying, and you can see that the first term, we can cancel out an s plus 2 and s plus 2 from top and bottom. And we're going to end up with just 1 over s plus 2. That's why it was better to do simplification this way, because we get a simple term. We have then plus 2 over s plus 2 squared, essentially, plus 2 over s times s plus 2 squared, plus e to the negative s over s plus 2 squared. So you can see we have 4 terms that we need to solve. So we need to do 4 separate Laplace inverses. Because basically, they have different things. Although some of them might have the same denominators, they have different things on the top, or just they're different at all. So you have first term, second, third, and fourth. And these are the numbers that I'm going to use to reference them when I'm solving each one of those. So let's continue solving those. Once again, this is just my answer in the S domain. This is not my final answer, so I need to go back, do a Laplace inverse, and find y of t. So for the first term, you can see we take the Laplace inverse of 1 over s plus 2. That is just e to the negative 2t. Plain and simple, nothing difficult. You can use the formulas in the book, and we get that. Solving for number 2, instead of doing a PFD, I can use the formulas, right, that are given in page 265. So if you look at your book, the one that we're using, you look for formula number 8 on that page 265, and it looks like this. And it says that the Laplace inverse of 1 over s minus a all of that square is equals to t e to the at. So for ours, our a, it's negative 2, right, because we have s plus 2, so then that will become s minus 2, so if it's with the formula. And we have 2 over s minus negative 2 out of that square. And then that becomes 2t e to the negative 2t. And that's solving for number 2. You can see that term number 4 is exactly the same. It has the same denominator, but on the top, it has an exponential. So that will result in a t-shifting. So if I see that, once again, we factor out exponential, we get the same, and the Laplace transform of it will be te to negative 2t times the unit step function and the t-shift. So wherever you know the values, let's put it in, and this is what we get. T minus 1 times e to the negative 2t plus 2 times u of t minus 1. And once again, you can see that the negative 2 was distributed times t minus 1. And then to solve number 3, we need to do partial fraction decomposition because this one has like different parts. So we have 2 over s times s plus 2 square. So we haven't seen this, something like this yet when in regards to PFDs. But whenever you have a terms that's square, you know, the whole thing is square. And I don't mean s to the square, I mean s plus 2 square. Of course, we could have factored this one out and work it out the same thing and get our two fractions that either or would have worked. If we keep in the simplified form with the s plus 2 out of its square, instead of only getting two terms, a over s and then b over something, right? Because of the square, this is how it works out. We have a over s, of course, because of the s there. But the s plus 2 square, you can see instead of once again only having one term, we have two. One where it's just s plus 2, and then one where it is s plus 2 square. Let's say this was s plus 2 cube, we'd have s plus 2 plus s plus 2 square plus s plus 2 cube. And that's just how it is. You can see after we do everything solving, it mathematically equals the same. So that's how it is. And you can see in this case, we have s plus 2 all of its square, but everything in the parentheses is to the power of 1, s to the power of 1. So in the numerator, we also have a constant as opposed to cs plus something else. Once again, this is a way in which we can be solved. But if you wanna, avoid doing this, getting confused, you can always also just do basically FOIL the s plus 2 square. You wanna get the original equation s squared plus 4s plus 4, and then you can do that, and you will have a over s plus bs plus c over s squared plus 4s plus 4, and you still end up with your three terms a, b, and c in a way. So either or method that you can do, it's valid. In this case, I opted for this method in PFDs. So after I take the Laplace of this one, you can see I'm going to get a plus b e to negative 2t plus ct e to negative 2t. And as you can see, this clearly resembles a ODE, if you remember back from chapter 2, a ODE with a case 2 where, the both roots are the same, which essentially is what we're getting here. So it makes sense that we get that. You can always remember, you can always check your solutions by doing any other methods, for example, constant coefficients, and see if what you get is actually correct. All right, so once again, let's do PFD. So we'll have this 2 over s times s plus 2 all of its square is equals to a over s plus b over s plus 2 plus c over s plus 2 to the square. Where after I multiply everything, you can see if I cross multiply, I cross multiply everything, and I divide by it, this is what I'm essentially gonna be getting. So as times s plus 2 square plus bs times s plus 2 squared and cs plus 2 square. All I'm doing here is I'm multiplying the top of 2s times s plus 2 squared times everything else, so that then we can start simplifying and solving. So this is just how it is for PFD involving this type of things. If you struggle to understand, you can always pause the video, do it yourself, and see how you can manipulate some of this algebraically to solve for the constants. So continuing, after we simplify everything, we're gonna get then a s plus 2 square plus bs times s plus 2 plus cs. You can see some of this essentially will simplify. And you can see, well, if you want, let me get back to what I did. So all I did here is basically send this s times s plus 2 square multiply times everything on the other side. So I send this one on the bottom to the top. So I need to do it for both sides, right? So that's why I did it here on the top and for this one, and then I simplify and I was left with this. So what I did was multiply times s times s plus 2 squared. So I can cancel the bottom and everything here. So we simplify. So this one, we technically did not do cross multiplication. Okay, so continuing, we can simplify, and this is what we get. And I want to get my three equations. So for the constants, I get for a equals to 2, where a, of course, equals to 1/2. For the s, I get for a plus 2b plus c equals to 0. And for the s squared, I get a plus b equal to 0. So starting for this, I get b to be negative 1/2 and c to be 1. So if I plug that into the already solved Laplace inverse, the general one, I will get 1/2 minus 1/2 e to the negative 2t minus t e to the negative 2t. So I will put all my solutions together. You can see we have e to the negative 2t plus 2t e to the negative 2t plus 1/2 minus 1/2 e to the negative 2t minus t e to the negative 2t plus t minus 1 e to the negative 2t plus 2 times the unit step function of t minus 1. So you can see some of these terms will basically combine. We have two terms that have the e to the negative t. So we have 1 minus 1/2 e to the negative 2t. So 1 minus 1/2 is just positive 1/2. We have 2t e to the negative 2t minus 1t e to the negative 2t. So they'll combine. 2 minus 1 is just 1. And then everything in the unit step function, remains the same. So solving it, this is my final answer, which is 1/2 plus positive 1/2 e to the negative 2t plus t e to the negative 2t plus t minus 1 e to the negative 2t plus 2 times u t minus 1. And this is my final solution for this Dirac problem. So once again, this one didn't have to be, it is not that complicated because we shouldn't Laplace. This one just happened to be longer, so we could have used Dirac or the function. But this one just was like this because of the inputs that we had, not because of the Dirac function or anything. So that is it on these videos. Hopefully, I hope that this was helpful for everyone. You can continue watching these Laplace videos. We're gonna continue now with other topics following this. But once again, if you have any questions, go back. You can ask me. But until the next time, good luck.